In the vast universe, there are plenty of mysteries, and one that has puzzled astronomers for a long time is the concept of dark matter. Dark matter constitutes 27% of the universe, but despite possessing powerful telescopes like the James Webb Space Telescope, scientists have been unable to detect the presence of dark matter. Recently, however, something unexpected has happened. This theory completely rejects the idea of the existence of dark matter and challenges our understanding of this mysterious substance present throughout the universe. What's interesting is that this theory is endorsed by none other than the legendary physicist Sir Roger Penrose, who believes that dark matter doesn't exist. So why is this theory forcing scientists to re-evaluate the standard model of cosmology? Why does Sir Roger Penrose believe that dark matter doesn't exist? Let's find out. There is this dark matter that seems to be out there, which dominates the material of the universe. It's by far the majority of the material substance in the universe. It's called dark matter, but nobody really knows what it is. It seems to be the major part of the mass of a galaxy and was first observed because of the stars going around too fast, which requires compensating for the extra attraction of this dark matter. That's how it was first observed, and all sorts of cosmological observations tell us it's there. Now, if it's there, and if it's really gravity because it's picked up on the gravitational degrees of freedom, there's nothing else in physics going on with regard to it. It tells you something about what it ought to be. One thing it ought to be, and I think I've listed these things here, if you can read them, one thing it ought to be is its mass. Well, the only thing it can be, if you've just got gravity roughly speaking, is a thing called the Planck mass. It might be 8 pi times it or something like that, but it's of the order of a Planck mass. How big is the Planck mass? It's about 10 to the 5th grams, which is about the mass of the eye of a flea. I believe I got that from Google or something. Now, that is huge if you're talking about particle physics. Imagine looking at the night sky filled with galaxies, stars, and cosmic wonders. It's a breathtaking view, but did you know that what you see is only a small part of the cosmic story? Dark matter, as the name suggests, doesn't shine or emit light. It doesn't interact with the forces that allow us to see celestial objects. It's nearly invisible, yet it's believed to make up about 27% of the universe's mass. This invisible enigma has puzzled scientists for years, and we infer its existence from the gravitational effects it has on the visible universe. Think of the universe as a giant jigsaw puzzle, and dark matter is the missing piece that completes the picture. It's like you can't see the piece, but you can see the gap it fills. The mystery deepens when you realize that, despite our belief in dark matter, we're not entirely sure what it's made of or how it behaves. In particle physics, there's no elementary particle that represents dark matter. This means we've been searching for something that has remained elusive, a cosmic mystery. Scientists have suggested various candidates for dark matter, from weakly interacting massive particles to actions and sterile neutrinos. These are like missing characters in a cosmic story, and we've been on a quest to find them. Big experiments like the Large Hadron Collider and projects like CISST, LUX Zeppelin, and the Axion Dark Matter experiment have been trying to unravel the mysteries of dark matter by capturing its elusive particles. Yet, despite years of searching, these efforts have mostly been met with silence. The lack of direct evidence for dark matter has led scientists to a profound question: what if dark matter isn't the answer? What if it's not the missing piece of the cosmic puzzle but rather a gap in our understanding of the universe's fundamental forces? This is where the theory of AQUAL comes in. Instead of persistently searching for dark matter particles, AQUAL proposes a daring alternative: we might need to rethink how gravity works on cosmic scales. The conventional understanding of gravity, as formulated by Isaac Newton, has been reliable in explaining the movements of celestial bodies. However, AQUAL suggests that there might be more to the story, especially at cosmic distances and low accelerations, where the laws of gravity might need some adjustments. AQUAL, which stands for a quadratic Lagrangian, is a theory that changes Newtonian gravity by introducing a new perspective on the gravitational force. The idea is to go beyond the traditional understanding of gravity and explore the possibilities of a more nuanced approach. In AQUAL, gravity is described not by familiar laws but by a different set of equations involving a general function and a threshold acceleration term. This suggests that when we look at the universe on cosmic scales, especially in regions with very low accelerations, we should observe a different behavior than what classical gravity predicts. It's like we're adjusting our perspective on the cosmos, searching for a new angle to understand its mysteries. So, what fuels this quest for an alternative theory like AQUAL? It's the unwavering curiosity of scientists and their determination to uncover the secrets of the cosmos. For almost a century, we've relied on the existence of dark matter to explain gravitational anomalies in galaxies and the structure of the universe. However, the lack of direct evidence has prompted us to reconsider our approach. Now that we've introduced the concept of dark matter and the intriguing alternative theory AQUAL, let's dive into the history of dark matter and understand its role in our understanding of the cosmos. The story of dark matter began back in 1933 when Swiss astronomer Fritz Zwicky made a discovery that would change the course of cosmology. Zwicky was an astute observer of the universe, and his focus was on galaxy clusters. These massive gatherings of galaxies, held together by gravity, are like cosmic cities, each with its own unique characteristics. While studying the Coma cluster, Zwicky stumbled upon a puzzling discrepancy. He realized that the observed mass of matter in the cluster, determined by studying the motion of the galaxies within it, didn't match the mass calculated based on the brightness and the number of galaxies in the cluster. In simpler terms, something was missing. It's akin to having a jigsaw puzzle where the pieces you can see don't add up to the complete picture. Zwicky, however, didn't brush off this anomaly. He proposed that there must be some unforeseen form of matter in the cluster, something that doesn't emit light or interact with electromagnetic forces. He named this mysterious missing element dark matter. This marked the first step in the dark matter puzzle, raising fundamental questions about the composition of the universe. The enigma of dark matter deepened with the entry of the American astronomer Vera Rubin. She, along with her colleague Kent Ford, turned their attention to a different aspect of the cosmos, the rotation of galaxies. In celestial mechanics, it's a common rule that objects farther from the center should move more slowly. It's similar to the way planets in our solar system orbit the Sun. Those farther away move at a slower pace. This is a fundamental principle of gravity. However, Rubin and Ford noticed something unusual when they looked at the motion of stars in galaxies. Instead of following the expected pattern, the stars in these galaxies were moving at increasing speeds as you moved away from the center. Think of it like a carousel, where the outer seats spin just as fast as the inner ones. This defied conventional logic. It was as if there was some unforeseen force at work, an influence that affected the outer regions of galaxies differently. Rubin and Ford arrived at a conclusion similar to Zwicky's. To explain this unexpected behavior, they suggested the presence of unseen matter, which they too referred to as dark matter. It was becoming increasingly clear that dark matter was not an isolated anomaly in the Coma cluster but a pervasive mystery influencing the dynamics of galaxies across the cosmos. As time went on, more pieces of evidence began to fall into place, strengthening the case for dark matter. In the 1980s, astronomers observed a phenomenon known as gravitational lensing. This happens when the gravitational pull of massive objects, like galaxy clusters, bends the light from background objects, such as distant galaxies. The way this bending occurred supported the idea that dark matter was present in these clusters, acting as an invisible gravitational lens. Another piece of the puzzle came from the study of the cosmic microwave background, the afterglow of the Big Bang. Measurements of the CMB revealed a universe that was clumpier and more filamentous than what would be expected if it were solely composed of visible matter. The existence of dark matter was becoming more than just a theory, it was an essential part of the cosmic narrative. This cosmic narrative is ingrained in what is known as the Standard Model of Cosmology, where dark matter plays a significant role. The Standard Model of Cosmology is our best attempt to explain the universe's origin, evolution, and current state. It includes the concept of dark matter as a fundamental component of the cosmos, accounting for a substantial part of its mass and influencing how galaxies are spread out. However, there's a hitch. Despite all the evidence, we're still in the dark about what dark matter is composed of. In the realm of particle physics, where we dig into the fundamental building blocks of the universe, there isn't a particle that represents dark matter. It's like having a character in a story who's present throughout, affecting the events, but remains faceless and nameless. This enigmatic character is what scientists have been tirelessly searching for. They've proposed various candidates, each with its own characteristics. Leading contenders in the quest to understand dark matter include weakly interacting massive particles, WIMPs, massive compact halo objects, actions, and sterile neutrinos. To hunt for these elusive particles, scientists have undertaken ambitious experiments, often deep underground, to shield against interference. The Large Hadron Collider, LHC, a massive particle accelerator, has been at the forefront of this quest, attempting to create dark matter particles under controlled conditions. Alongside the LHC, experiments like CIESST, LUX Zeppelin, the Axion Dark Matter Experiment, and dark matter maps from the Dark Energy Survey have all contributed to the mission to uncover dark matter. Despite these efforts, a shroud of uncertainty still hovers over the existence of dark matter particles, as if the enigmatic character in our cosmic tale remains concealed behind layers of cosmic mystery, refusing to step into the spotlight. Given the prolonged silence from the dark matter front, it's no wonder that scientists have started to question the narrative. What if, after all these years, dark matter isn't the solution to the cosmic puzzle? What if it's not the invisible force holding galaxies together, but rather a gap in our understanding of the fundamental forces that govern the cosmos? This line of questioning has led to the exploration of modified gravity theories. One such theory, modified Newtonian dynamics, MOND, takes a different approach. Instead of searching for invisible particles, MOND suggests that we should rethink how gravity works on cosmic scales.